So our first speaker of the day is Zhengchao Wan, who will be speaking to us about computing the Gromov-Hausdorff distance between ultrametric spaces.
Okay, thanks for the introduction. Today I'm going to talk about computing the Gromov-Hausdorff distances between ultrametric spaces. So this is a joint work with Facundo Memory and Zhang Smith, and this work was supported by NSF grants. You can find details of my talk in our archive paper, and some codes are also available in our GitHub page. So the Gromov-Hausdorff distance is a natural distance between matrix spaces. So starting from two matrix spaces, you can first isometrically embed them into some ambient space and compute the Hausdorff distance between their images within the ambient space. If you infinize the Hausdorff distances over all isometric embedded in the ambient spaces, then you obtain the definition of the Gromov-Hausdorff distance. The distance has been used in differential geometry for studying manifold convergence, and recently found its application in shape analysis, and also in applied topology for establishing stability of topological invariance. One natural question to ask is, how hard is it to compute this distance given finite matrix spaces? Schmidl studied this problem in his PhD thesis. He found that computing the Gromov-Hausdorff distance is in general NP hard with respect to the cardinalities of spaces. And moreover, he found that the hardness still holds even if we restrict to the collection of finite ultramatrix spaces. So what is an ultramatrix space? An ultramatrix space is a special matrix space which satisfies the strong triangle inequality. A strong triangle inequality is a modification of the usual triangle inequality by replacing the addition with the maximum. And we will use a UX instead of DX to represent an ultramatrix in my talk. Ultramatrix spaces are highly structured. For example, every 3 points in an ultramatrix space will form an isosceles triangle. And for any two closed balls in an ultramatrix space, either they have no intersection or one of them must contain the other. Moreover, ultramatrix spaces are related to a notion called dendrogram in hierarchical clustering. So a dendrogram is a function from the half-real line into the set of all partitions of a given set X. And it is required to satisfy the following conditions. Instead of going into details of the conditions, I will use a figure to explain the essence. So here's a dendrogram over a set of 3 points. And the axis is labeled the half-real line. So when the parameter is very, very small, then the dendrogram will just give you the singleton partition. And when the parameter is increasing, the partition generated by the dendrogram will become coarser and coarser. And eventually, when the parameter is large enough, the dendrogram will return the trivial partition. Ultramatrix spaces are actually equivalent to dendrograms. More precisely, given a finite set X, there exists a structure-preserving bijection from the collection of all dendrograms on X to the collection of all the ultramatrix on X. To illustrate a little bit, given the dendrogram theta, and let U be its image under the map, then for any 2 points X and X prime, the distance U of X and X prime is actually the smallest number such that X and X prime belong to the same block in the partition theta of T. For example, here is a dendrogram over 3 points, and these 2 points A and B will agglomerate together at parameter 1. So their corresponding distance is 1. And similarly, the distance between A and C is 2. I hope I have convinced you that ultramatrix spaces are kind of special. And even though computing the Gromov-Hausdorff distance between ultramatrix spaces it's in general NP hard, I still want to leverage the properties of ultramatrix spaces to identify some alternative of the Gromov-Hausdorff distance that's easier to compute between ultramatrix spaces. And this is our first goal in the talk. Our second goal in the talk is the following. I want to identify some collections of ultramatrix spaces over which the Gromov-Hausdorff distance is easier to compute. Before stating our results, let me first provide an alternative formula for DGH, which may be best known to many of you. So a correspondence R between two sets X and Y is any subset of the product space such that the restrictions of the canonical projections to R is surjections. So there's a theorem saying that for matrix space X and Y, the Gromov-Hausdorff distance is 1/2 times the infimum of distortions of all the correspondences. And the distortion of a correspondence is defined in this way. Now let's start to talk about the first goal. That is to identify easier to compute Gromov-Hausdorff type distance between ultramatrix spaces. Actually, we have identified a one parameter family of Gromov-Hausdorff type distances by replacing the distortion part with the so-called P distortion, and P is a parameter from 1 to infinity. So recall that in the definition of the distortion, this term should be the absolute value of the difference between these two terms, and then we replace this difference by the P difference defined using the formulas above. And note that when P equals to 1, the formula here actually coincides with the formula before for the usual Gromov-Hausdorff distance. We prove that for each P, this DGHP is a matrix on the collection of isometric classes of compact ultramatrix spaces. We also found something special when P equals infinity. So recall the definition of the Gromov-Hausdorff distance. It is defined by infimizing the Hausdorff distances over all ambient matrix spaces and isometric invariance. When the input spaces are ultramatrix spaces, the originally studied the quantity UGH by modifying the previous formula by restricting the infimum to be the set of all ultramatrix ambient spaces instead of all matrix spaces. And this new quantity UGH turns out to be an ultramatrix on the space of all compact ultramatrix spaces. That's something very interesting. And later we found out that actually our DGH infinity coincides with the UGH distance. And from now on, we will use the symbol UGH instead of DGH infinity, since UGH better indicate that the distance is an ultramatrix.
Zhengchao, can I ask a quick question?
Sure.
Could you go back to the prior slide? So is it obvious or maybe easy to see that for a pair of ultrametric spaces, there exists at least one ultrametric space in which you can embed both of them into it?
Yeah. So think of two ultrametric spaces as dendrograms. Then you can just draw a large link between two dendrograms. And the new dendrogram will be a common ambient space that contains the both ultrametric spaces.
Oh, that's very clear. Okay, thank you very much.
No problem. And this figure summarizes our results about computational complexity of the family of distances. It turns out that for any P finite, the DGHP is NP hard to compute, whereas when P equals infinity, UGH can be computed in polynomial time. And in the next few slides, I will explain the green part. For that purpose, I will introduce the so-called T-close equivalence relation on ultramatrix spaces. So any 2 points are identified together if and only if the distance is bounded above by the parameter T. And this is actually equivalence relation. This equivalence relation will induce a quotient space X sub C of T and a quotient metric. And this quotient matrix space is also an ultramatrix space. And let me explain the T equivalence relation using the dendrogram. So first, the figure on the right shows the equivalence classes under the T close equivalence relation. So points with the same color are from the same equivalence class. And figure on the right shows the dendrogram for the quotient space. Actually, the dendrogram is obtained by simply forgetting all the details below parameter T. So this is the dendrogram you get. Then I will say our first main result, that is the structural theorem for UGH. It turns out that the UGH between two finite ultramatrix spaces is the smallest parameter T, such that the T close quotient of X is isometric to the T close quotient of Y. This theorem allows us to reduce the problem of computing UGH to essentially scanning over all possible distance values of X and Y and checking tree isomorphism. I will use the figure to explain the process for computing UGH. So here you have two spaces, X and Y, and then you first consider the largest the distance value R. You take quotient, and then you have two quotient spaces. They're isometric. So you move on to the next distance value. You take quotient, they're isometric. You continue the process until the first time W. When you see the two quotient spaces are not isometric, then you move back one step. Then the parameter T is the ultrametric distance, the UGH distance between X and Y. So the number of distance values depends linearly on the cardinality of X and Y. And to check isometry between an ultrametric spaces is equivalent to checking isomorphism between trees, which can be done in polytime. So therefore, the whole process described here can be done in polytime. This explains the green part. And more precisely, if you let n to be the maximum of cardinalities of your input spaces, then UGH can be computed in O n log n time. Now I will turn to our second goal, that is to identify collections of ultrametric spaces over which DGH can be computed easily. To compute DGH, we first solve a simpler problem, the decision problem. So given finite ultrametric space X and Y and the parameter epsilon greater than 0, the problem to solve is whether there exists an epsilon correspondence between X and Y. And an epsilon correspondence is a correspondence with distortion bounded above by epsilon. There are two base cases where the problem can be solved immediately. So case 1, if the difference between diameter values is greater than epsilon, then there exists no epsilon correspondence. Case 2, if the maximum of the diameter value is bounded above by epsilon, then any correspondence is an epsilon correspondence. And note that if one of the space has cardinality 1, then the tuple X, Y, epsilon belongs to one of the base cases above. In order to solve the decision problem for non-base cases, we will introduce the T-open equivalence relation as an analog to the T-closed equivalence relation. So under this relation, 2 points are identified together if and only if the distance is strictly smaller than T. And we in particular care about the partition induced by this equivalence relation. We call this partition the T-open partition. And here is our second main result in our paper. So given two finite ultrametric spaces X and Y and the parameter epsilon greater than 0, and assume that X, Y, epsilon, the tuple doesn't belong to one of the base cases, then you let delta 0 to be the diameter of Y, delta epsilon to be the diameter of Y minus epsilon. Then consider the delta epsilon open partition of X and delta 0 open partition of Y. Then there exists an epsilon correspondence between X and Y if and only if there exists a surjection from the index set from 1 to nx to the other index set J from 1 to ny. And also this surjections require that for each index J, there exists an epsilon correspondence between Y sub J and the union of X sub I, where I belongs to the pre-image of J. To help you understand the theorem, here is a graphical explanation. So here is the space X, here is the space Y. We consider the open partition of Y at its diameter value, and then it's partitioned into two sets. And then consider delta epsilon open partition of X, and X is partitioned into three sets. And then consider a surjection indicated by this graph. Then, if there exists an epsilon correspondence R1 between X1 and Y1 this pair, and if there exists a epsilon correspondence R2 between this pair, then if you take union of these two epsilon correspondences, you will get an epsilon correspondence between the whole space X and Y. So the main purpose of the theorem is the following. It can convert the problem of solving a decision problem with input X, Y into a series of decision problems with smaller input. And this way, it inspires us to consider a recursive algorithm to solve the decision problem. So in case you don't know what is a recursive algorithm, here's a simple example. So a recursive algorithm is an algorithm that will call itself with smaller input. And here's a recursive algorithm for computing the nth Fibonacci number. So when n is the 1 or 2, the base cases, the algorithm will return 1 directly. And otherwise, it will invoke itself and with smaller input n-1 and n-2. And we will use a similar idea to devise a recursive algorithm, which returns an epsilon correspondence between ultrametric spaces x and y whenever it exists, and returns 0 otherwise. And here goes the theorem, the algorithm. So the first part basically says that if the two spaces are in one of the base cases, we determine the correspondence directly. Otherwise, we take open partitions according to the parameters specified in the structural theorem. And then for each surjection and for each index, we'll invoke the algorithm itself with some smaller input spaces specified by the structural theorem. In order to analyze the complexity of recursive algorithm, a standard tool to use is the so-called master theorem. Basically, if you know the number of subspaces and you know the size of each subspaces, then the master theorem can tell you what is the total time complexity of a recursive algorithm. And in our case, the size of a subproblem is the cardinality of an input space. And in order to control the size and the number of subproblems that were generated by our recursive algorithm, we introduced the so-called first epsilon gamma growth condition. So an ultrametric space satisfies the first epsilon gamma growth condition if for any point x and any t greater than epsilon, the cardinality of the t closed equivalence class of x is bounded above by gamma times x, the t minus epsilon open equivalence class of x. So here are two examples. Let's consider this one. This y will satisfy the first epsilon 2 growth condition. For example, a closed class here has 4 points, the cardinality is 4, but its open class here has only 2 points, so it satisfies epsilon 2 growth condition. But for this one, it doesn't satisfy the epsilon 2 growth condition because a closed class here has cardinality 4, whereas the open class here only has 1 point. Then we prove that even if our ultrametric spaces satisfies epsilon gamma growth condition, then our recursive algorithm with input x, y, epsilon can be implemented in polynomial time. Here's a drawback of our recursive algorithm. That is, it will perform many repetitive computations. For example, suppose xi's and yj's are some open equivalence classes generated by our recursive algorithm with some input. And let's consider these two different surjections. For each of them, you have to invoke find correct with the input x4 and y3 and epsilon. And this results in repetitive computation. And this turns out to be a common phenomenon for all recursive algorithms. For example, if you want to compute the Fibonacci number, Fibonacci 5, using a recursive algorithm, well, eventually you need to compute Fibonacci 1 for twice and Fibonacci 2 for 3 times, etc. So one idea to avoid such repetitive computation is to use the dynamic programming idea. So basically, you just need to use a big table to store the values you have computed. Then you don't need to compute again. Under the guidance of the idea of dynamic programming, we modify our recursive algorithm to a dynamic programming algorithm. And I will skip the details of the algorithm, but just state the result. So we also identify the second growth condition, which is weaker than the first growth condition. And we found that if two ultrametric spaces x and y both satisfy the second epsilon gamma growth condition, then the dynamic programming algorithm can be implemented in the following time complexity, where n is the maximum of the cardinality of x and y. So a complexity of this form reveals that our algorithm is the so-called fixed parameter tractable, which means the complexity is of the form of a product where the coefficient depends on some parameter of your input spaces, but the exponent here is a constant independent of your parameter. And then based on our algorithms for solving the decision problems, it's not hard to design an algorithm for compute the exact value of Gromov-Hausdorff distance. And our final result is the following. Suppose you have two finite ultrametric spaces which satisfy the second epsilon gamma growth condition. And suppose their Gromov-Hausdorff distance is bounded above by epsilon over 2. Then the Gromov-Hausdorff distance can be computed within the following time complexity. And which means that computing the Gromov-Hausdorff distance is also fixed parameter tractable. We have implemented the recursive algorithm and the UGH algorithm by MATLAB, and you can find some code in the GitHub. And I can show a quick demo how to use our code. So after you download all the functions from our GitHub page, there are several test functions you can play with. For example, this is a test UGH code. You're first generated two random ultrametric spaces and compute their the UGH distance. And let me show you another one. This one will also generate two random ultrametric spaces, and we'll compute an epsilon correspondence between them with a pre-specified epsilon value. And here's a summary of my talk. So first, we identify a one-parameter family, DGHP, of Gromov-Hausdorff type distances between ultrametric spaces. And second, we prove that whereas for each finite P, DGHP is NP hard to compute, DGH infinity can be, or UGH can be computed in polytime. And third, we construct an FPT of fixed parameter tractable algorithm for computing DGH between ultrametric spaces. The references of my talk can be found here, and I want to also mention two future or ongoing directions. So this UGH distance is the ultrametric version of the Gromov-Hausdorff distance, and so it's natural to consider what is the ultrametric version of Gromov-Hausdorff distance. And you can see the drawing work with Facundo, Axel, and Christoph. We post something recently on arXiv about this direction. And another interesting direction to pursue later for the future is that how can we extend the results of DGH between ultrametric spaces to a more general class called tree matrix spaces? Yeah, that's the end of my talk, and thank you for your attention.
Thank you so much, everybody. Please unmute yourself and applaud Zhengchao.
Thanks.
So, are there any questions for our speaker?
I have a question.
Yeah.
So, do any of these distances, like are any of these distances the interleaving distance? Because you said that an ultrametric space is the same thing as a dendrogram, so you could also look at the interleaving distance. I'm wondering if your algorithm gives you some algorithm to compute the interleaving distance in some like tractable way.
That's an interesting question. So first of all, we did consider interleaving distance. Let me go back to this slide. So we consider a family of DGHP distance. We also actually identify a family of like P interleaving distance between dendrograms. And there is a basically for say DIP, P interleaving distance is Lipschitz equivalent to DGHP. Oh, sorry, my theory just. Okay, and when the interesting thing is that when P equals infinity, the infinity interleaving distance actually agrees with DGH infinity. That's something you can find in our arXiv paper.
Right. So your algorithm allows you to approximate the interleaving distance then, like the usual
Yes.
standard interleaving distance? Okay.
Yes.
Up to some constant.
Constant 2. Yeah.
Right, right.
I had a question, Zhengchao. So you described how this for any P, this gives a metric on the isometry classes of ultrametric spaces, right? But
Yes.
when P is 1, you can also do that on metric spaces, right? That's the
Yes.
standard. So I was curious if you could say what goes wrong when P is bigger than 1 and you try to define a distance on isometry classes of metric spaces. Like what property does it break? Or, can you say, it's not quite a metric, but does it have some of the metric properties or?
It is still, just for simplicity of the talk, I would say it's for ultra matrix spaces. Also, the distance holds for the whole matrix spaces, for the whole collection of matrix spaces.
Oh, so this is still a metric for P larger than 1. It's still a metric on the isometry classes of metric spaces. I see. Cool. Yeah. Thanks.
No problem.
And I also have a quick question, actually. So at the end, you have this growth condition, which actually seems, I'm not sure if I'm on to judge, it seems fairly reasonable in the sense that when you imagine phylogenetic trees, they do have, they do sort of tend to, if you go down a little bit, there's usually a very small fraction of the branches that they collapse very quickly. Have you tried applying this yet to any data sets of phylogenetic trees?
No, not for this work. And actually in this one, in this work about ultrametric Gromov-Hausdorff distance, we do apply to phylogenetic trees. We studied some data from what is it called, flu or something. Yeah.
Very interesting.
So it's definitely applicable to such a data set.
Very interesting. Thank you so much.
No problem.